Hi, I'm Kevin Whitley. I'm a biophysicist here at Newcastle University. And so I use microscopy to look at how bacterial cells divide. So we all know that bacteria can sometimes cause infections, but that usually those infections can be treated with antibiotics. But bacteria are developing resistance, and so treatments that used to be effective no longer are, and new antibiotics are urgently needed. A lot of antibiotics target bacterial cell division. How bacteria divide is they use complex nanomachines that dynamically interact together to build a micron scale wall in the middle of the cell. And so I want to look at how these nanomachines work in the middle of the cell while they're living and dividing. The problem is bacteria are really tiny, and to make matters worse, a lot of bacteria are rod-shaped, and so when you image them on a microscope, they lie horizontally, and so the division ring is viewed side-on. It's hard to see. But wouldn't it be great if you could stand the bacteria up vertically and then peer down bacteria and see the division ring in a single imaging plane? So what I wanted to do was to take bacteria, confine them in what we call microholes in the middle of a microfluidic chamber so we can image division protein dynamics while perturbing the system with specific drugs. So how do I do this? Well, I put on my bunny suit, I go to a clean room, and I nanofabricate some small micro pillars to use as a mold to make these micro holes. We then make the micro holes on the back of a microscope cover slip and then confine the entire thing in a sophisticated microfluidic chamber that's made out of double-sided tape and epoxy. And so when this chamber is finally assembled, we have the cells in there and we put them in the microscope. And then we can image division protein dynamics in high resolution while perturbing the system with division-specific drugs. And so I use this and other methods to look at a division protein called FTSZ, which is a core part of the bacterial division machinery, finding that it's important initially to set up the constriction process, but then becomes dispensable afterward. And so this contributes to our knowledge of how the complex bacterial division machine works, and also to the development of new antibiotics.